Frank has an encyclopedic knowledge, I would say, of all things concerning the present state of superconducting qubits and their progress towards systems. But tonight he will focus on one point, variational algorithms, and I'm blocking my own screen, and quantum computer co-design. Please, Frank.
Thank you. So this is a bit of an adaptation of the kind of an adjustment of the title I put into the program, but it's following the same ideas of the abstract. So thanks a lot for inviting me. I've learned a lot during this week. I mean, we had experimental days and more mathematical days, and probably today can help us having, with the talks of Alexandre and me, to have a bridge of, theoretical physics that touches both. Now, this is my group, and as you see on the left, we are working on various projects on gate-based quantum computing, on quantum annealing, and on quantum control. And the talk is a little bit motivated by what happens if people who are working on these different things are in the same building, talk to each other, and try to discover parallels between their work, which may provoke some thoughts. Also, you clearly see this photograph on the right is pretty old because we are not properly socially distancing. So I want to first kind of motivate why co-designing, so why designing hardware and algorithms together is something we should still do and think about. When I say this leads to not quite universal quantum computers, I mean devices that typically in the mathematical sense can be universal, but where the cost of embedding a certain algorithm or a certain programming paradigm is very asymmetric. So there are some things you would not like to do on this. Why we should still think about this, even though there's a big trend nowadays, also driven by companies, to offer like standardized platforms and do all processors. I will give you two examples from papers of ours which this can do. One is an architecture where no wires cross for a calculation for something called variational self-energy, and I will explain you why you should care about this concept. I will then show a newer paper where I want to discuss how you can make the QAOA algorithm with only single qubit controls to co-design. Then I will make an excursion in something we are very proud of, which is a way to get high gate fidelities on given hardware, and then put two things together because you will see that this is actually based on very similar techniques than the implementation of QAOA, and think about what could be a good way to actually program a variational quantum algorithm on a suitable piece of hardware. So why co-design? Well, we are calling where we are now the era of NISQ. And I think one feature that everybody sees, even people coming from the world of application and computer science, is that when you even use the best platforms that are available, you do see properties and constraints of the hardware when you're implementing things. You need to do error avoidance, and there's sometimes a qubit not working in their connectivity. So my kind of favorite analogy here is a picture of my first computer I ever owned, the one on the left. Person on the right is the brains behind the company Sinclair Research. It was a genius of British engineering. And with those computers, which had 1 kilobyte of RAM, my 13-year-old self discovered after a very short time of owning it that I can really do more if I learn assembler, and I learned a lot of, say, how the ROM was done. And I think, so I very early learned how to program following architecture. And I think, this is what we should still cherish in this era, to really get kind of the best impact out of what the hardware research, which on the one hand is progressing enormously, but on the other hand, still has a long way to go, can currently offer. And one connection that is kind of easy to see how these things are connected is 2-qubit gates versus physical interactions. Following the truism that if we want to make a 2-qubit gate, which naively, where we say, okay, we make a gate by exponentiating a Hamiltonian for a certain time. More practically, we're using a cleverly designed time-dependent Hamiltonian, and we're solving the the time-dependent Schrödinger equation. But on both of the time evolution operators on the right, sorry, I don't have a mouse pointer, so I will talk you, so this somehow doesn't seem to work on my computer. I will talk you to where I would like you to look. So clearly, if I, with these expressions for U gate, want to make a 2-qubit gate, I need a term in the Hamiltonian that's non-trivial in both qubits. So I need a physical interaction, as shown in the Hamiltonian sketch on the upper right, which is kind of grouping single and 2-qubit terms. And in one of the early papers discussing a path to quantum supremacy, this was kind of put visibly very succinctly. This was the first version of the random circuit leading to a Porter-Thomas distribution from Google, where you obviously see that the 2-qubit gates are all between neighboring qubits because this was meant to be compiled on a chain. So the interaction was nearest neighbor on a chain, and it was shown that this is actually enough. But then, as we know, and as we've seen in this conference, still a different solution was chosen for good reasons. And another case of co-design that we can look at is quantum annealing. So I think this was introduced many times before and probably wouldn't have this introduction anyway, but let me just point you on what I want you to see on the left. Quantum annealing, in a way, has a very simple way of controlling the system with typically one global field only, which is encoded in this function A of S that is slowly blending us from the driver Hamiltonian HD at time 0. In the bottom of the left column, you see the requirements of the annealing schedule, to the problem Hamiltonian on the right, where the solution, the problem that we want to solve is encoded. This is diagonal on the Z basis, the driver has in the X basis. So we need much simpler controls, and in adiabatic quantum computing, the kind of close cousin, or you could call it a subset of quantum annealing, we even have the constraint that we vary this very slowly, and certainly this has evolved a bit. But let's just look at what this does to chips. So I'm showing pictures of gate model hardware. I think this 9-qubit chip from John's group is still extremely popular because there is still everything open, and it's a beautiful picture. Of course, the modern things are encapsulated for good reasons. No worries about that. But even if you are, there's probably a more experimentally oriented crowd today also, but even if you look at this not knowing a lot about hardware, you see that there is high frequency wiring, there are these separated wires, there are the little wiggly oscillators on top of the cross, which are all needed because this thing is operated under a fast clock with microwaves. And if you look at a typical cryostat insert, the steampunky logo of modern quantum computing, on the right, this is something from our Open SuperQ project. You see that there is this gigantic wiring assembly, which is needed to get high frequency signals in and out. On the bottom figures, you see pictures of the D-Wave chips, which got encapsulated much earlier and which are aiming at implementing the quantum annealing paradigm. So one thing you see in the middle figure is there are these golden long qubits, not delocalized crosses, which intersect at coupling points, because in quantum annealing, a lot of the coding is done in physical interactions. The problem Hamiltonian needs to encode a complicated coupling problem, which you can avoid by using swap gates and gate model. You see on the left, but this is kind of not a very clearly, it's not quite so clear to see what's going on because of this type of picture. You see that next to the long stretch lines of qubits, there are these little rectangular coils on top, and there's a lot of other elements put right on chip, which are used to pre-program the the processor, which do not need to be kept away because the coherence requirements are different. And also on the right, you see that this wiring assembly is not as elaborate as for the gate model quantum computer. You can go with much more simpler wires that only carry low frequencies because you do not need this high frequency precision. So if you want, quantum annealing is an extreme co-design of a quantum computer that is meant to implement these type of quantum algorithms. And now, of course, the big thing in the NISQ era, which we heard a lot about yesterday, are variational algorithms, where, like in a hybrid bike, for example, we use the scarce resource, which in the hybrid bike is the content of the battery, which for quantum computer is the quantum computer coherence for the things that absolutely need to be done there. And you're integrating this as a classical algorithm, which is much cheaper, that sends new parameters to the quantum algorithm as shown in the upper panel. And of course, on the bottom, there is a sketch of the QAOA or algorithm, where essentially the prefactors of the problem and driver Hamiltonian are also determined by a classical algorithm. And this is a prime candidate for quantum simulation. And we can ask, if we want to implement these things, are there also suitable co-designs? Let's go through one example from my group. It's a bit older, but I think it's worth repeating, which is to go from molecules to materials. We have seen in Chris Monroe's talk that when you want to simulate a molecule, what you really simulate is a curve like on the upper left, and specifically look at the bottom curve. This is the energy of a molecular bond, in this case in lithium hydride, as a function of distance of the two nuclei. And finding the minimum gives you the bond length, and the depth of the minimum gives you the binding energy, the energy that holds the molecule together. And if you, the moonshot of this community is to simulate the molecule on the bottom, actually to simulate the core. This is ferredoxin, 2 iron, 2 sulfur, which plays an important role in photosynthesis, which we humans would like to imitate. Now, the variational self-energy method is aiming at solid state materials, like, for example, high temperature superconductor. And even though we learn that in quantum computing, if we have in a molecule, if we have n orbitals, we only need a number of qubits that's polynomial in the number of orbitals. We wouldn't want to do this here, because for solid state materials, the number of constituents is controlled by Avogadro's number, 6 times 10 to the 23, and even a polynomial, this is prohibitive. But as we learned from Phil Anderson, who's pictured here and who recently passed away, going from a molecule to a material really changes how you should look at this. Actually, just to appreciate Phil Anderson in this community, you know, when I'm really trained as a condensed matter physicist, and he's like a towering figure of this. And I think it's fair to say that he invented the statement that things like the Hubbard model describe condensed matter physics. Before the era of Phil Anderson, when you did condensed matter physics or the state physics, you needed to describe a concrete material and not a model system that describes a lot of other systems. So in this system, the energy doesn't have, and the bond length doesn't tell us as much as it does in a molecule. And we have looked at specifically the Hubbard model, which is a model with a very rich phase diagram, which is believed to model some aspects of the physics of high temperature superconductors. So what you want to get is the phase diagram on the right. You want to see where is this antiferromagnetic, where is this superconducting, where does this have all its other phases. It's a complicated model, but it has been well studied. So this is a valid way to try out how to simulate a material on a quantum computer without needing 10 to the 23 qubits. And what we want is, we do not want to really compute the energy. We want to compute something like the Green's function. So the Green's function shown on top is an interesting object in Manybody theory. And you need to read this expression in the angular bracket kind of from right to left, because this is how time goes. Psi dagger means you take your Manybody system and you're putting in an electron at position r prime at time t prime. Psi means you're taking it out at position r in time t, and then there's some time ordering going on. So this really tells you what does a single electron do in the Manybody background, and it helps you to, for example, find out in which phase you are. Now in superconductivity, this is actually a matrix, and we're using spinors. But the really interesting thing is that we are now essentially looking at the energy not of a single particle, but at the energy and the physics of a particle moving in our solid state system. And in fact, there's an object called the self-energy, shown by the Feynman diagrams in the middle of the left column, where a electron essentially has an energy contribution that's coming from everything around it, and you're summing up the interaction with the environment repeatedly, and you get this Feynman diagram expression. And the interesting thing is that this self-energy, this generalized energy, if you want, now also satisfies a variational principle, in that the derivative of the thermodynamic potential omega, the grand potential, with respect to the self-energy, satisfies a saddle point condition. This is called the variational cluster method. And to now keep them, so you now can use an ansatz for your self-energy the same way as you use an ansatz for your molecule, and try to find a solution for this expression with the ansatz. Now, the ansatz you're using is you're taking your lattice, you're chopping it into little pieces shown in H prime that you're solving exactly, and then you're using an approximate method that is sketched on the bottom to build the whole lattice out of these little clusters. And the method gets more and more precise if these clusters get bigger. And the idea of our algorithm was now to take the solution of the cluster that you need to be exact onto a quantum computer, and then do the variational equation classically. And this is the co-design this is leading to. If we go back to the Green's function, if you break down the Green's function into qubits, this is essentially an out-of-time correlation function. So you have, you digitize the the psi into qubits, you measure it at different times, you measure this correlator, for which it's sufficient to have a single probe qubit with measurement connected to one chain of qubits that contains the state of the Hubbard model. You can efficiently deal with the swapping overhead there, and you need a second chain that you use for simulating finite temperature. And what is interesting is that no wires cross in this architecture, and making wires cross in the superconducting chip is a big challenge. It's, as we have seen by Google now, a solved problem, but it's still very inconvenient. And on the right, we show that if you look at the second line from the bottom, that with 55 qubits, you could already use do these clusters that are 3 by 3 by 3, and that would outperform classical computers. So here, kind of a long prelude, there is a co-design. Now let's look at the second one, QAOA with only single qubit controls. The preprint we have on this is actually called approximating the quantum approximate optimization algorithm. So the QAOA was introduced yesterday. It consists of taking the driver and the problem Hamiltonian that I've shown with quantum annealing and applying it in an alternating fashion, and then use a classical optimizer to find optimal times for which you apply these algorithms until your readout in the end gives you a satisfactory solution. So it's a variational algorithm for combinatorial optimization problems, and it requires that the driver and the problem Hamiltonian can be switched to implement the gate sequence. So, and it's factorized adiabatic. So this is too complicated. We want to make it simpler. So the first thing is that we realize that we try what happens if we are actually never switching off the problem Hamiltonian. We let it run all the time, and we simply, and we want to implement the algorithm. So first of all, implementing the problem Hamiltonian, which for a reason that will become clear in a minute, we call the resource interaction, that will actually, the time to implement this will simply be given by the waiting times between the single qubit gates. Now, the single qubit gates that we are running while the interaction is switched on will not have the same effect. There will be an error by the simultaneous presence of both Hamiltonians. To control this error, we introduce a speed ratio, alpha being the Rabi frequency over the interaction strength. So the Rabi frequency is the strength of the single qubit drive, and the interaction strength is the size of the problem Hamiltonian. And if you estimate the error, it scales as alpha squared times n squared, where n is the number of qubits. it turns out that this is too pessimistic. We have done simulations over random instances of QAOA, and we got this color-coded picture. It has a bit of structure in it, which means we should have taken even more instances. But what you can see is that at a speed ratio of above 100, it turns brownish, which means that our simpler QAOA, hardware-efficient QAOA, is actually slightly better than the regular QAOA, whereas on the left, it gets a bit worse by up to 10%. So even if we are on the left, if we are at 10 to the 1, we get, a decrease of about 4%, which may even still be acceptable, but in some cases, we even get improvement. So why is this so? Why did our analytical estimate do so badly? Well, because of the real question we are asking here. The real question we are asking in QAOA is to go from a well-defined initial state, everything in sigma x, to a target state that gives you a good approximation of your optimization problem. And for this, you're dialing in your parameters beta and gamma. Even if during the application on the drive, on the middle panel of our simplified QAOA, of our approximate QAOA is slightly wrong, the optimizer, the classical optimizer, can partially compensate this by choosing the right value, different values of the angle. You do not want to implement the QAOA exactly. You just want to make sure that your structure is rich enough so you can reach the target state. And if you need to express it slightly differently, if you get slightly different parameters, this is totally acceptable. It's not that you have an algorithm where you need to precisely follow a recipe. So this is quite unique to variational algorithms that is so tolerant for the simplified implementation. We could go even further. So what we could do now is essentially use D-Wave's idea to preset the interactions on the chip and not touch them during the computation, thus greatly reducing the number of high frequency lines that need to go, because you do not need to pulse couplers anymore. You can slowly program them. And another thing you could do is, if you were able, and in some platforms that may be possible, I think Rydberg is a good candidate, to essentially make a constant all-to-all interaction, shown here as a resource Hamiltonian, you can use fast single qubit X gates to, there's a typo in this formula, the first XK should be an XL, to essentially conjugate this Hamiltonian around the X-axis. And by carefully choosing the times at which you apply several pairs of X gates, TLM, you always need to switch on 2 single qubit X gates, you can actually cut down the resource Hamiltonian to your problem Hamiltonian. So from your interactions RJK, you need to go to your to your problem Hamiltonian GJK. For this, you need to find the application times TLM. And in the paper, we show that this is a simple matrix inversion problem that is solvable, and it goes as number of qubits squared. So this way, you can actually avoid controlling your 2 qubit interactions altogether, as long as you have them. And again, this may hopefully inspire new co-designs. So here are 2 cases where we can make hardware simpler if we decide that these variational algorithms what we like to go to. Also, we have shown that we can compile this efficiently. Here is an example of compiling the algorithm properly. And given that you're running the interaction and the single qubit gate simultaneously, it even gets a bit shorter because you need fewer single qubit errors, but that's a bit of an aside. So now for something completely different. And so it seems. Now something that happens in a different office in my group, namely lower error rates with optimal control. So here is kind of the optimal control gospel that we have been talking about for the last 15 years. If you have a Hamiltonian with some uncontrolled term H0 and some control fields Ui and some controlled Hamiltonians Hj, these can be your microwave drives and things like this. And if you want to force the time evolution to make a gate by the solution U of Tf at the final time of your time-dependent Schrödinger equation, you can use numerical variational calculus to adjust your pulse shape so it does what you want under optimal conditions. Now, the problem with this field you can see on the right. This is from work that we've actually done with John in a project together with John in the pre-Google era. This is a very fast way to do a 2-qubit gate for a resonator. And what you see is that the pulse shape is quite complicated. So if it works, it's good. But if it doesn't work, it is very difficult to debug, because if you understand your error, you don't quite know how to change the pulse shape to accommodate for this. Now, in the past, and I'm telling this because I will show an example how to improve this, there was a successful application of quantum optimal control that has to do with leakage reduction. In the popular transmon that you see on the left, we have this ladder of energy levels, and the detuning of the 0 to 1 transition relative to the 1 to 2 transition, that's the number called delta 2, is not really big. So if you're driving your system fast, like shown in the middle, the spectrum of your driving pulse on the 0-1 transition may actually overlap with the 1-2 transition and drive it also. But we showed that by applying a drive where you're shaping the cosine omega t of your resonant drive and the sine omega t at the same time, and where the envelopes follow this little differential equation, so one is the derivative of the other, you can reduce this by a lot. And it's for me kind of a point of pride that this PRL is now in most experimental control softwares a checkbox. You say you want to do drag, and it's doing drag. Now, this works really well because it has few parameters. So the software that is running at modeling experiments could very easily implement this. Because with this simple parameterization of this optimal control, you can calibrate everything on the experimental toolkit you have everywhere, and then do an experiment. So why would you not do this with fully optimized pulses? Well, because they are complicated, and because applying a complicated pulse requires that your Hamiltonian on the right is known precisely, that there is absolutely no uncontrolled degrees of freedom, here also called junk, that the whole filtering setup that goes from room temperature to the chip is completely characterized and stable, which to the precision needed is very difficult to do. That and some of the energy levels shown on the right in the round box are actually really, really hard to pinpoint completely, which is why applying a non-intuitive pulse like the one on the left is usually impossible because of all these uncertainties. Now, I should say that specifically in the world of cat qubits, actually people do apply these optimal control pulses efficiently. In this case, the system is very well characterized, and the pulses operate on a relatively narrow bandwidth for which the experimentalists are able to find a good model. But now we want to be as fast as possible and use larger bandwidth, so we have to do something else. And here is a recent result, a preprint of this March that has actually worked. So what you see in the upper left is the typical drag strategy. You see the red line is the envelope of your pulse. The blue line is its time derivative. This is what you use in usual drag. And now we have used numerical optimization with 55 parameters to actually push this curve a lot further. What you see in the lower left is the pulses that are coming out, which are really quite far deformed from the upper left. But you also see the randomized benchmarking results, panels C and D, that show that with the piecewise constant parameterization that we've used here, we get a lot less error, specifically at short times, compared to the simple drag. And this is also sampled on the right. At some point, you see on the right, the fidelity is going down because drag is running into its limit, whereas our solution saturates essentially until the drive power is so high that there is strong nonlinear responses of the equipment. And this is an experiment done at IBM in Switzerland. Now, the reason why I'm making this interlude is that I want to share a little bit with you the long period of research that went into it. Specifically, if you look at the loop on the left, we have essentially followed the workflow where the experimentalists first design your system, they characterize it. We numerically give them a couple of pulses by a normal optimal control method. And then by measuring fidelity with randomized benchmarking and in situ pulse updates, we are calibrating the experiment without having a model. This requires that your pulse is simple, and we have found a gradient-based optimizer shown on the left that doesn't only give you piecewise constant pulses, but that this directly allows you to optimize Fourier components, because typically a Fourier representation with a gentle envelope like the one shown in the middle is the most efficient and the most sparse and parameter economical way to describe how to drive a quantum system. It's not time slice gates. Typically, we are getting towards these AC solutions. And on the right is something we are coming up with, which is essentially using methods from artificial intelligence to improve the closed loop part of the diagram on the left, and to also see what does the calibration actually teach us about the model. Can we, from the calibration data, learn more about the system that we need? So this is, if you want, AI-enhanced spectroscopy. Now, this had to go in there. I won't go through the details because that would be a whole different talk. But what you can appreciate is that the lower part of the left diagram is very similar to setting up a variational quantum algorithm. We are trying something, we measure our success, and then we update the way how we try based on our success. And what you also see on the right is that we have a way to deal with non-optimalities of the implementation that I have shown in the QAOA application, where we're not quite implementing QAOA the correct way, but we can compensate for this by choosing our pulses a bit different. So if you want to make an extreme statement, QAOA is a time discretized, a bang-bang version of pulse update, and it's an algorithm version, an algorithm level of pulse update. So it's on a whole processor and a whole algorithm, not just on a single gate.
Frank,
and,
10-minute time check.
Okay, I'll be done in 3 minutes.
Yeah. Okay.
I would like to put this observation in a bit of a more of an extreme way, and suggest the following. If we look at QAOA on a very superficial way above, we are having a couple of gates, and we are choosing variational parameters to switch on operations rapidly in time, to apply rapid single qubit gates. And statements about variational algorithms being universal typically have to do with having enough parameters to reach every potential output state that we would like to do. So this is essentially a statement about controllability. Are the resources that I have general enough so I can do everything I want? Now, the way how I propose to look at QAOA, bringing in tools from optimal control, is shown in the bottom, where essentially we are not slicing up the application of driver and of the paths that we need to actually reach universality and programmability, not time discrete, but in a way that is as efficient as possible, that can be parameters of sine and cosine waves. And again, what we need is essentially a guarantee that our setting is rich enough to do what we like it to do, to get a final state that offers us a good solution of the problem we're interested in. So there is again a statement about controllability and probably also constraints, and this in control theory jargon is called the reachable set. And I feel that if we have hardware that's general enough, the bottom approach can help us to get higher performance and to get closer to some type of true disruption. So this is kind of not even a summary. This is also trying to segue into a discussion. I think that the software on and for quantum computers, so by software on quantum computers, I mean algorithms that we would like to implement, and software for quantum computers, I mean the stack below it, including the optimal control tools that I've shown you to calibrate gates. Those need to be closely integrated also for things like low latency in order to implement these algorithms in a good way. And I think this is a software part of co-design that goes with the hardware part of co-design, which I try to convince you is trying to leave things that are out that are unnecessary for the application I have in mind, with the goal that I will not, I don't have to build them and I can scale more aggressively. We can even take this further and ponder the thought, namely that adiabatic quantum computing, gate model, and this quantum control approach are probably three initial programming paradigms motivated by physics for the adiabatic theorem, computer science, because this is how we like to think about computers, and chemistry, which is where quantum control was mostly pioneered. And I would like to advocate for exploring the spaces in between and to look at much more hybrid programming solutions, because ultimately these approaches, as much as they can be proven to be very powerful, in order to be practical, they probably, they're coming from a tradition, and probably the most efficient way to program a limited quantum computer is a hybrid of the three, and we should find it. That was a pretentious ending. Thank you very much for your attention.
Okay, thank you, Frank. So we are open for discussion. I have in my own list, I have actually just a rather technical question, but let me pose it to you. In the early part of your talk, you introduced a variational principle concerning the grand potential, which is interesting. Could you explain why, or is there a simple understanding of why it's a saddle point extremum problem rather than a minimum?
I do not have a really simple explanation for that. No, this is coming out of a long calculation. I have no simple explanation, sorry.
But it is a fact that it's not a minimum. It's really a saddle point.
It's typically a, no. So we say saddle point metaphorically as an extremum.
Okay.
As a point that satisfies this equation. So yes.
Okay. Okay.
And so I should also say this method on classical computers was not invented by us. The big names around this are Michael Potthoff and David Sénéchal. The latter, I think, being actually a Sherbrooke colleague of our previous speaker.
Okay. So any further comments or discussion of this contribution? There's something in the chat which I find totally incomprehensible. Sorry, Q&A, I mean. Luckily, it's still Mr. Anonymous or Miss Anonymous. What quantum laptop commercial? Oh, well, maybe I missed something. But does anyone know what that means? I guess not. Okay.
I think they're asking whether or not we will have commercial quantum laptops. And I think I can answer that on Frank's behalf and say it will be a very long time.
Okay.
I would even augment that. The most powerful computers most people use in their daily lives are the ones that navigate them around the city traffic, and they are not owning them. They're accessing them through the cloud. And I would argue that this is probably also the right place for the quantum algorithms we currently know about. So if it's a long time, and I'm not worried about this. In the post-PC world, we are moving computing power to somebody else's computer, which is the honest version of saying the cloud. And that is not so I think the quantum laptop is also not really a goal.
I'm just going to summarize what Frank just said and ask, why do you want a quantum laptop? I think what you really want is a quantum computer that works.
Yes.
So are there more questions about the talk just given?
Maybe I have a question to Frank. So this co-design sounds nice, but so like as a theorist, you say, well, if I had that connectivity that you're showing there on the current slide, that would be great. But then, the current labs that are making qubits, they don't provide that. So how do we go about that then?
Yeah. I mean, the idea is that these co-designs are trying to remove elements that are hard to make for current labs. And, we can argue the D-Wave is an extreme case as they're putting a lot of units on the chip because they do not need to do that much with them. Now, to go about this, so first of all, people could make it their mission of building the perfect QAOA machine. QAOA is in principle universal, and see whether they can really scale more aggressively. If we could also think about, if we're looking at co-designs that still require microwave drives, is to build an experimental setup that is standardized, that has a couple of low frequency lines, that has a couple of high frequency lines, that has a microwave tied box, and that has a very well-defined interface. So the whole setup, the cryostat, the wiring are always the same, and then allow to connect the different chips to it. But at the moment, I would say it's mostly if somebody wants to build a Hubbard model solver or a QAOA machine, they could basically make a bit faster progress by studying these ideas. And a lot of the other things actually would not change. It is also probably, it could encourage people to think about hardware that otherwise was difficult to use. And to think about elements that could be used for always-on interaction. So, for example, connect a lot of flux qubits to one common loop that connects them all to all, and use single qubit gates to remove them. And by this way, again, make progress, scale faster.
Okay, so I think we come to the end now of the seminar, the presentations of this evening and of the whole week. So we have just a wrap up and a panel discussion. And let me begin a little bit with the panel discussion to the remote age. And I'd like to thank Ashley. Ashley had been on, but I think she's off again. But like to thank all the staff that worked hard, and of course Omid for keeping us our computers all in order as we come to the end of the week here. So I think, well, let me actually ask the organization. Are we going to just record straight through, or are you going to take a break, or you indeed record the final panel as a discrete event?
Are you asking me, David?
Omid, say that again.
Yeah, are you asking me?
I am, yes.
Yes. So yeah, my plan was to stop recording and then start again at the panel.
Okay, so I think you can stop now. And then within a few minutes, we'll be ready to launch the panel.